Hey everyone, Mrs. V here, and today we are going to learn how to write equations for combustion reactions. These are my very favorite types of reaction because I love to burn things. So let's get on and learn some of the chemistry of this reaction. We did a reaction where we compared petrol, kerosene, and ethanol as fuels by putting a little bit of each of them into separate evaporating dishes and lighting them up and seeing what happened. It was a lot of fun. Let's have a look at the results from that reaction. So we used petrol, which is of course the fuel for motor vehicles. We used kerosene, which is jet fuel, and we used ethanol, which is a component of Formula One fuel. So we're looking at the different ways that they burned. We looked at three features of their burning. We looked at how easily they ignited. We looked at what the flame was like and how much smoke was produced when they burned. So here's the results. Petrol ignited very, very easily. Now, what makes a fuel ignite easily is that it turns into vapor very quickly because you don't actually light the liquid in a fuel. You actually light the vapor. So if a fuel can make vapor very easily or turn into a gas very easily, then you're going to have a lot of gas above that fuel, and that's going to light up very quickly. Of course, the heat from the flame is going to create more and more of that vapor, and you'll end up burning the whole fuel sample. Kerosene, much more difficult to ignite. In fact, you have to drop the match in. You've got to leave it in the fuel for quite a bit of time. And the match will start acting as a wick, drawing some of the fuel in. Eventually the match burns out and the fuel itself ignites. But you've got to actually put a lot of extra heat in to get enough vapor for that to light. So that's quite difficult to ignite. And that's because kerosene has a higher boiling point than petrol does. Ethanol was quite easy, probably not as easy as petrol, but still pretty easy to ignite. You didn't have to throw the match into the actual fuel. It would have lit before the match actually hit the fuel. All right, as far as the description of the flame, the petrol has a very large flame. It's a yellow flame, and the petrol burned reasonably quickly. When we got to the kerosene, the flame wasn't as big, but the kerosene burned for a long time. With ethanol, the flame is very interesting. It's much less visible. It's sort of a bluish color. Just the tip of the flame is still yellow. This is one of the problems in Formula One refueling, is that you cannot see the flame. So if there's a mistake in refueling and somebody is actually on fire, it's difficult to see the flame. So it's difficult to see they're on fire. And so one of the dangers of Formula One. All right, the amount of smoke. Petrol burns, the flame is quite smoky, and after the burning's finished, the evaporating dish has quite a lot of carbon in it. The soot that's left behind is just carbon, comes from incomplete combustion. So all of the smoke is from incomplete combustion, and kerosene had a much smokier flame, lots of smoke being produced, and at the end, the evaporating dish was totally covered in a layer of black soot. So that produces a lot of carbon. So it's very much incomplete combustion occurring there. With ethanol, however, the flame is not particularly smoky at all, and there's very little soot in the evaporating dish when you're finished. Right. If you don't have those results down, pause the video and write them into your book, please. When writing equations for combustion reactions, the elements inventory method is not your best choice. It works very nicely for the other equations that we've been writing, but combustion equations, it can actually be quite messy to use the elements inventory method for this. So I'm going to show you an easier way to write your combustion equations. And of course, you can use this method for all equations if your mind works in that way. Right, we're going to focus on complete combustion. I'll do a separate video on incomplete combustion for you, but we're just going to focus on complete combustion today, which is the kind of combustion where there's plenty of oxygen and the products are always carbon dioxide and water. So I have an example here. This is an example of the combustion of candle wax. So this is candle wax. Candle wax would be a mixture of many different compounds, but one of them is C25H52. Now, the way we're going to approach this is using the law of conservation of matter. And of course, you remember that says that matter or atoms cannot be created or destroyed during chemical reactions, which means every single thing that's there at the start has to be there at the end, and everything that was there at the end had to be there at the start. So we're going to use the fact that if you have a look at candle wax, all of the carbon atoms in the candle wax have only one place to go in the products. They can only end up as carbon dioxide. And all of the hydrogen atoms in the candle wax can only end up in the water. And from there, once we've got our carbons and our hydrogens sorted out, we can start to think about what to do with our oxygens then. We don't ever start with oxygen in a combustion equation. You're going to get yourself into all sorts of trouble. In fact, you're going to have a bad time. So let's have a look at balancing this particular equation. So I've got C25H52. It's hard to believe a molecule could be that large, but they actually come much larger than that. I know it's reacting with oxygen because combustion means reacting with oxygen. Because it's complete combustion, I know that my products are carbon dioxide and water. I know that I have 25 carbons in the candle wax, and all of them have to go into the carbon dioxide. And because there's only one carbon in carbon dioxide, that means I must need 25 CO2s. When it comes to the hydrogen, I have 52 hydrogens in my candle wax, and they all have to go into the water, which means because there's 2 hydrogens per water, I'm going to need 26 hydrogens. 26 water molecules, sorry, to get the 52 hydrogen atoms. When I get to this point, I can start to tally my oxygens. So 25 CO2s, every CO2 has 2 oxygens, so there's 50 oxygen atoms in there. 26 water molecules, each one has 1 oxygen, so that makes another 26. So my total number of oxygens over here is 76. When I go over to the oxygen in the reactants, I can see that each oxygen molecule has 2 oxygen atoms. So in order to get 76 oxygen atoms, I'm going to need half that number of oxygen molecules. So I'm going to need 76 over 2. Or, of course, you can simply just go 38. And now my equation is balanced. And that would have taken quite significant effort in the elements inventory of running back and forth between sides. So I find that method easier. Let's have a look at the equations that we used in our experiment. So in this case, we're going to, again, only look at complete combustion. So we're going to start with petrol. Petrol contains octane. We're looking at combustion, which means reaction with oxygen. And because it's complete combustion, then we're going to have carbon dioxide and water as our reaction products. Now in petrol, there are 8 carbons. All of those carbons have to be in the carbon dioxide, so I need 8 CO2s. I have 18 hydrogens, all of them need to be in the water, but remember, water's already got 2 per molecule, so I'm going to need 9 H2Os there. Now I do my tally. So 8 CO2s gives me 16 oxygens, 9 H2Os gives me 9 oxygens. Altogether then I have 25, which means I'm going to need 25 over 2 of our oxygens, or 12.5 of them. Now that's looking a little ugly, isn't it, having a fraction? It doesn't really matter if you have a fraction in balancing an equation. We just haven't met that before. It's a perfectly legitimate way to balance an equation. But let's make it look nice and tidy by multiplying throughout by 2 to get rid of that fraction. So we need 2 octanes, and 25 over 2 times 2 is 25 oxygens. And that's going to give us 16 CO2s and 18 H2Os. Now we just tidy that up by putting the states in. So octane is a liquid, oxygen is a gas, carbon dioxide is a gas, and water is a liquid. And there's our balanced equation, that reaction. I want you to have a go at kerosene. So I want you to pause the video and have a go at balancing the equation for kerosene, which is C12H26. Remember, combustion is reaction with oxygen. It's complete combustion, so we get carbon dioxide and water as our products. Now, pause the video and balance that one. No, I mean pause the video and actually do it. Okay, now let's have a look, see how well you did. So 12 carbons in the fuel means 12 CO2s. 26 hydrogens means 13 H2Os. Remember, there's 2 hydrogens in every water. Tally the oxygens. We have 24 from the CO2s and 13 from the H2Os. So altogether that is 37. That means that we're going to need 37 halves of the O2, and multiplying everything throughout by 2 to get rid of that ugly fraction. We get 2 of the dodecanes, 37 oxygens, 24 carbon dioxides, and 26 of the waters. Finally, putting in the states, kerosene is a liquid, oxygen is a gas, carbon dioxide is a gas, water is a liquid. How did you go? Did you get it all? Well done. Finally, ethanol. Now, ethanol is not a hydrocarbon strictly fuel. Ethanol is an alcohol. In fact, ethanol is the alcohol in alcoholic drinks. And they contain hydrogen, carbon, and oxygen. So if we look at the formula for ethanol, then it can be written in many ways, but let's just go simple as possible, C2H6O. And we're going to have combustion, which means a reaction with oxygen. It's complete combustion, so our products are carbon dioxide and water. And off we go. We're getting used to this by now. 2 carbons in the fuel means 2 carbon dioxides. 6 hydrogens means 3 waters. Do our tally. 4 oxygens from here and 3 from here. So our total is 7 oxygens that we need to find. Now comes the tricky part. You have to remember there's already an oxygen in the ethanol. So we only need to find 6 more to make up that 7. Now, this is going to trick some of you, and you've got to try and remember, whenever you're looking at an alcohol, there is already an oxygen in the fuel. So to make up 7, we need 3 O2s to balance that equation. All right, so that's the equations for your petrol, kerosene, and ethanol experiment. I will see you guys in the next video.